that the minimal polynomial f, actually let me stand aside for like 2 seconds so that you have the board there. Okay, good. So now put those two together. The fact that f, the minimal polynomial of alpha, splits over k and that those 4 are its roots, you see that the minimal polynomial of alpha over q is a product like this, where up to this point, it's possible to have some exponents here. Each of these factors could be raised to some power. That's the conclusion that you arrive up to, that you have up to this point. But now, well, one way to finish off the argument, the better way to finish off the argument would be to say that, well, you're in characteristic 0, so you know that the irreducible polynomials don't have repeated roots. So these exponents here, for the minimal polynomial, these exponents all have to actually be 1. Because your minimal polynomial doesn't have any repeated roots. So then you see that the minimal polynomial f is exactly equal to this polynomial h, and you're done. In particular, h is irreducible. Okay, very good. So now, this was the first part of the lecture. And now the second part, which was rather short, was the following. We started our next topic, which is roots of unity. And so let me do a recap of that as well, a summary of that as well. So now we're interested in roots of unity. Roots of unity. So we started by introducing a notation, the notation being the following. So if any field, so for any field f and n positive integer, denote or define mu n of f to be the set of all nth roots of unity in f. So the set of all alpha in f such that alpha to the power of n is 1. And now, first observation was that this is so no mu n of f is a subgroup of f star of order at most n. And the reason for that was the following. So you can very easily check that this is a subgroup of f star by checking the subgroup conditions if you wish. A better way, quicker way of seeing it would be to observe that mu n of f is the kernel of the map from f star to f star, which raise every element to the power of n. So the map from f star to f star, which sends any alpha to the power of n, well, that's a group homomorphism, because f star is a binary, and then its kernel is by definition this mu n of f, and hence it's a subgroup of f star. Why is the order at most n? It's because if you look at this definition here, this condition there, when you say alpha n is equal to 1, what does that mean? That means alpha is a root of x to the power of n minus 1. And then this is the polynomial of degree n. It can have at most n roots. So it has at most n roots. So mu n of f has at most n elements. So that was that. That is, so for any n and any field f, instead of n roots of unity in f, is a subgroup of the star of order at most n. And then the second observation was that, in fact, each of these things, each of these mu and f's is a finite subgroup of f star, right? Now, in fact, any finite subgroup of f star any finite subgroup of F star is of the form mu n of F for some n. Why? See, suppose G is a subgroup of F star, it's finite, well, so then it has some finite order, say of order n. Say of order n, and then the claim is that G is exactly equal to mu n of F. And the reason for that is the following. By Lagrange's theorem, so by Lagrange, indeed, by Lagrange, G is a group of order n, so the order of every element of it divides n. By Lagrange, G to the power of n is equal to the identity of the group, identity of F star is 1. By Lagrange, G star is 1 for every G in G. And then so you see that, so every element of G is an nth root of unity. So G is contained in mu n of F. But now, you say that, okay, see, this one we already know that it has at most n elements, right? At most n elements. This one, well, we're assuming that it has n elements. This one, n elements. Now, put everything together. So G is a subset of mu n. G has n elements. Mu n has at most n elements. Put those together, you'll see that G actually has to be mu n. Right, the point being that mu n can't have any element that is not in G, because, well, G has n elements. If it had any element that wasn't in G, well, then this guy would have more than n elements, but it doesn't. It has at most n elements. So G is just mu n. So, talking about the groups mu n is the same as talking about finite subgroups of F star. Okay, good. And then we have the following theorem. So before I state the theorem, let me remind you something about mu n in C. So if you think about the group of nth roots of unity in C, that group is it's got order n, and it's a very, very special type of group. It's a cyclic group, right? That's very important. It's generated by e to the power of 2 pi over n. Now, what we're going to show is that here's the theorem that in fact, for any field f, so let f be any field, then any finite subgroup of F star is cyclic. So the situation that happens in C that these finite subgroups, which are the same as these groups mu n, that these groups mu n are cyclic, that happens in general. Any finite subgroup of the multiplicative group of units of any field is cyclic. Okay, good. So now for the proof of this, right, so for the proof of this, we're going to give two lemmas. So we're going to give two lemmas, and one of the lemmas we gave in this lecture, in the next lecture at the beginning, we're going to give the second lemma, and then the proof is just going to come out of these lemmas very easily, the proof of the theorem. These two lemmas actually, they have they don't concern ring theory really. The statements are, well, the second one is group theory. The first one, the statement is elementary. The proof we're going to give is group theory. So you can keep this statement, this theorem, in the background of your mind, but you don't have to think about it right now. We just, the lemma we're going to give will, have, on the surface, won't have much to do with the theorem, but it will be actually useful. So here's the lemma. The first lemma is the following: that for any n greater or equal to 1 for any positive integer, the sum of phi of these, so this is Euler's function phi. Phi of d is the number of positive integers up to d, which are relatively prime to d. The sum of phi of d over positive divisor is d of n. This is just equal to n itself. So for example, if I take n to be 6, the positive divisors could be 1, 2, 3, and 6. And then if you look at phi of 1 plus phi of 2 plus phi of 3 plus phi of 6, this is equal to a 1 plus 1 plus a 2 plus 2. This is equal to indeed 6. Okay, now the proof of this statement, that was the last thing that we did in this lecture, in our Monday lecture. The proof is very quick if you use group theory. So here's the proof. It's really just this. It's just a consequence of the structure of cyclic groups. So let me give the proof here. Let G be a cyclic group of order n. Say Z mod n if you wish. Z mod n Z. Now, okay, so the number of elements of G, well, it's equal to n. Now, partition the elements of G based on their order. So put together all the elements of all the elements that have the same order. So I'm going to write this as the sum over D, all D, of the number of elements of the following set. Elements G of G such that the order of G is equal to D. Right, so you partition the group G based on the order of the elements. Now, because G has order n, the order of every element of G divides n. So here in this sum, I can just look at the divisors of n. This is because for every G in G, the order of G divides n. So it's equal to this sum now, and then the next step is the following. Okay, so sum D dividing n. Okay, the number of elements of G which have order D. G is a cyclic group. So here you didn't use cyclicity at all. This was, you just use finiteness. You just use the fact that G has order n in this first equality. Now, well, G is cyclic, right? Cyclic of order n. So what does that mean? So I have a cyclic group of order n. Now for any divisor D of n, how many elements of order D does my group have? Phi of the elements, right? By the results about cyclic groups. So this is because, G being cyclic of order n has phi of the elements of order D for every divisor D of n. So cyclicity was crucial in that step, and that completes this proof. So that finishes the first lemma, and then in the next lecture we're going to start by giving the second lemma and wrapping up the proof of the theorem, and then taking it from there. Okay, thank you.